Alright, welcome to the video on equilibrium of a particle. So, this is going to be very similar to the steps that we took in force vectors, except for now instead of just combining the vectors together, we're going to look at a particle and try to equalize all the forces on that particle. So, for example, if we have a box of some sort that is being held up by different cables, let's see, that's attached to the wall, and that's attached to the wall, and they're all connected there at the point. All right, we're gonna say that this box weighs 100 pounds. We'll give this a slope of a 4, 3, 5 triangle. And we'll say this is at 45 degrees. All right. So for this, the first step we always want to take in solving a statics problem is to draw your free body diagram. Since this is equilibrium of a particle, we can just free body diagram the point in which all the forces meet together. So that's going to be this point right here. You can visualize that. The weight of the box goes straight through that point, and so do the forces from the cables. And so we just need to look at that point. So looking at that point, we have a tension force coming out that way, and a tension force coming out that way, and then a tension force coming out that way. Now, these are all going to be different, so we're just going to label them 1, 2, 3. Labeling them doesn't matter. You can label them whatever you want, just as long as you keep track of them and you have it labeled on your free body diagram. That's all that matters. Just so we can match up our answers with a picture, then that's good enough. All right, so once we have the free body diagram of that particle, we can look at the free body diagram of the box itself. So we have this box, and we have the weight of the box, which we know is 100 pounds. Now that acts through the center of gravity of that box. So right through the center there. And then also holding the box up is that tension 3 force. Now this is very important because if we didn't have this tension 3 force, then the box wouldn't be held up by anything and it would just fall to the floor. But because everything is static, it's not moving, it's being held up by something. And from this picture above, we can see that the box is being held up by cable 3. And so this tension 3 force is holding that box up. Okay, so now that we have both of our free body diagrams, we can write equations of equilibrium. So we'll call this free body diagram 1 and free body diagram 2. So looking at free body diagram 2, if we sum all of our forces in the y direction, and we can just pick either up or down being positive, it's totally arbitrary, you're going to end up with the same answer either way. But out of, I guess, tradition or what's normal, I usually use up as positive. I like to stay consistent, so then that way it's always the same in your brain. You don't have to think about it. So for me, up is always positive. However, if you really want down to be positive, you can do that. You'll end up with the same answer. So if we sum those forces, we're going to get negative 100 pounds plus T3. Now, because this is static, the box is not moving, we know that the sum of forces in any direction have to equal 0. That is key to statics. The sum of forces will always, always, always equal 0. So we can take this negative 100 pounds plus T3 and set that equal to 0. Now, we can solve for T3, and we know that T3 is going to equal 100 pounds. Great, so now we have one of our unknowns. All right, so looking at free body diagram 1, we can now sum the forces in the X and Y directions, and then we can solve for our unknowns, just as we did on the first one. So I'll start with our sum of forces X, and I always like to do to the right as positive. Again, you can do the left, just stay consistent within yourself, so that way you're not thinking about it every single time. And as explained above, the sum of the forces are going to equal 0 because the system is not moving, it's static. So, sum of the forces in the X direction, we're going to have negative T2 times the cosine of 45 degrees plus T1 times 4/5 equals 0. Now, the reason that this is 4/5 is because we're given the slope of this cable rather than an angle. And so we want the X component, so we take 4, which is horizontal, and then place that over the hypotenuse. And then that's the ratio of, that'll give you the portion of X in that rope. Okay. So now we can do our sum of forces Y equals 0. Again, I like to use positive as being up. So we're going to have negative T3 and plus T2 sine of 45 degrees plus T1 times, in this case, we want the Y component, which is the 3. So we're going to do times 3/5 equals 0. So now that we've got this, we know what T3 is, so we can plug that in. We have negative 100 pounds plus, at this point, I just like to get everything into numerical values. So I'm just going to plug in sine of 45 into my calculator, which is going to be 0.707 T2 plus 3/5 T1 equals 0. All right, so we're gonna call this equation 1 and this equation 2. So now if we look at this, we've got two equations and we have two unknowns, t1 and t2. So because we have the same number of equations as our unknowns, we can solve the system of equations for our unknowns. There's a couple different ways you can do this. Again, totally personal preference. You can solve it any way you want. I'm pretty sure we learned how to solve a system of equations in like algebra maybe. My favorite way is probably to set up a matrix, or you can do it by elimination. Again, whatever you like to do best. Also, in some of the fancier calculators, they'll solve a systems of equations for you. I think I'm just going to do it by elimination. So I'm just going to rewrite my equations down here. Again, I'm going to plug cosine of 45 into my calculator, which should end up being the same thing as sine of 45. 0.707 T2 plus 4/5 T1 equals 0. And when you rewrite this one, you're going to want to put it in the same order that you have. Like you're going to want to do your variables in the same order as you did your first one. So it's going to be 0.707 T2 plus 3/5 T1 equals 100 pounds. Now we can take this and we can add these equations together, and these will cancel, and we'll be left with 7/5 T1 equals 100 pounds. So T1 equals 100 pounds times 5/7, which is going to end up being 71.4 pounds. So now we have T3 and T1. So now that we have T1, we can go and plug that into either equation 1 or equation 2 and then solve for T2. It doesn't matter which one you plug it back into, they'll both give you the same answer. Or at least they should. If they don't give you the same answer, then you made an algebra error somewhere. So I'll just use equation 2. So 0.707 T2 plus 3/5 T1, which we have now, which is 71.4 pounds, equals 100 pounds. So then when we solve for T2, it's going to equal 100 pounds minus 3/5, 71.4 pounds, all divided by 0.707. You can just plug that into a calculator. And I get 80.8 pounds. So then we have T2. And it's as simple as that. So we know in order for this box to be in equilibrium, one, two, three. Okay. Right. All right. So in order for this box to be in equilibrium, we know that cable 1 must have a capacity of at least 71.4 pounds. Cable 2 has to have a capacity of at least 80.8 pounds, and cable 3 has to have a capacity of at least 100 pounds. So if you were designing this system, this rope system, where it had to carry a box that was 100 pounds, these are the limits that your cables would have to be. So you would go in and you'd figure out, okay, a cable with a diameter of 1/4 inch can carry this many pounds. Is that enough? Is that more than this right here? All right, so that's kind of the purpose behind why we're trying to figure out the tension in these cords so that later on you can design a system. Now, another thing that might happen, or another scenario, I guess, that you'll be asked to figure out is, let's say we know the cables have a tensile capacity of, let's just say, 50 pounds. How heavy can the box be without failing the cables? So in this scenario, you might be going in and looking at a system and it's already built, it's already set up, and whoever owns this specific system says, hey, we want to come in and put something new here. Is that okay? And you have to be able to go in and evaluate if the new weight is going to be suitable for the cables that are already present. For example, in a gym, if somebody's going to go in and replace hanging basketball hoops, you've got to go in, look at the system, figure out the capacity of that system, and then compare it to the new basketball hoops weight and see if it's going to be able to hold that weight, if it's going to be adequate or not. So we've got this system, and we want to know how much weight this system can hold, knowing that that max is 50 pounds, and same with that, and same with that. All right, so we're going to start off the same way. We're always going to draw our free body diagrams. So this time I'm going to start in the same place that we did last time. Start with this particle here. Boom. 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 T3. It's 1. T2. And then for our box, T3 and weight. So okay, so our next step is going to be to write equations of equilibrium. So again, we're going to start with our second free body diagram, and we're going to go sum of forces y equals 0 because nothing's moving. We need it to be in equilibrium, so negative w plus T3 equals 0. And we know that the maximum amount that T3 can be is 50 pounds, right? Yes, 50 pounds. You know what, I'm gonna change this a little bit. Say cables, 50 pounds for 1 and 2, and cable 3 capacity equals 30 pounds. Okay. So from that we know that cable 3 is going to have a capacity of 30 pounds. So negative w plus 30 pounds equals 0. So w is going to equal 30 pounds. Now, at this point, you might think, okay, we're done. We have w. Let's move on. But we need to follow it back up through free body diagram 1 and make sure that T2 and T1 don't exceed their capacities of 50 pounds. So we're going to look at free body diagram 1. Sum of forces x equals 0. We're going to choose to the right being positive. Again, you can choose to the left, whatever you're more comfortable with. And so we're going to have T1 times 4/5 minus T2 cosine 45 equals 0. And sum of forces in the y equals 0. I'm going to choose up being positive. Again, you can choose down if you're more comfortable with that. We're going to have negative T3 plus T1 times 3/5. Making sure I have that right. Yep, times 3/5 plus T2 sine of 45 degrees equals 0. And we'd solve for T3, which was, well, we're given T3, which we decided in the previous step was 30 pounds plus 3/5 T1 plus 0.707 T2 equals 0. That equation 1, that's equation 2. So 4/5 T1 minus 0.707 T2 equals 0. 3/5 T1 plus 0.707 T2 equals 30 pounds. We add these equations together. 7/5 T1 equals 30 pounds because these cancel. And we can solve. T1 is going to equal 42 pounds. So this is the force that is acting in cable 1. And we were told in the problem statement that cable 1's capacity is 50 pounds. So the tension that we calculated, the actual tension acting in that cable is, is less than our capacity. So therefore, we are okay, because 50 pounds is our limit and we are under our limit. So the cable is going to be okay. So now we've got to solve for the tension in cable 2. Again, you're just going to pick whatever equation you want. I'm going to use equation 1. So T1, which we know is 42 pounds, times 4/5 minus T2 times 0.707 equals 0. So T2 equals 47.5 pounds. Again, which is less than 50 pounds, which is our capacity. Therefore, okay. Because 50 pounds is the limit and we are under our limit, so it's okay. So, because both of those check out, we know that max weight of box has to be 30 pounds. All right. So again, just to recap, the only thing that we're really trying to accomplish with this section is to show you that we are looking at a specific point in a system that all the forces pass through, and we're going to sum the forces up to equal 0 and then solve for our unknowns. And those unknowns are the things that are keeping this system static. They're keeping the system from moving. And so you might look at this and say, okay, this is 100 pounds. What does it matter what these forces are? Why? Who cares? You know, what difference does it make? but it's really important when you get a few classes in design. You need to know what force is acting in this cable so you know how big the cable needs to be. If you just throw a cable up there, one, it might be too small and it might snap under the weight, or it might be too big, which is wasteful, it's not economic, and you're spending more money than you need to. So we want to hold everything in equilibrium so things aren't moving in space. We like things to be stationary. And this is how you're going to find those forces. As always, if you have questions or comments, you can email me at Taylor's Tutoring, etc. @gmail.com, or use the contact us button, or there's also a chat function at the bottom of this page. And we'll get your questions or comments answered. If there's a specific problem that you're struggling with, a specific question that you have about this example or a homework problem you're working on, go ahead and visit our homework help page, and we can answer specific questions for you there. If you would like to sit down and really go over this stuff in depth, you can visit our tutoring page, and we can do an online tutoring session where I can chat with you online, or we can video chat, whatever you're more comfortable with, and we can go through these things step by step, answer questions there as well. If you are in the northern Utah area, we can do an in-person session where we can sit down together and we can go over this stuff. Again, any questions, comments, concerns, feel free to contact us anytime.